We're continuing with the BC FRQ worksheet on Taylor series. This is worksheet number 2. We're looking at number 3 and 4 in this video. So number 3 here, the function f has derivatives of all orders for all real numbers x, and we're given some value of a function and its derivatives all the way down to the third derivative at 2. Part A says write the third degree Taylor polynomial for f about x equals 2 and use it to approximate f of 1.5. So first things first, we're going to write the third degree Taylor polynomial. What we can do is we can build this Taylor polynomial using Taylor rule or formula, which is if I want to find, for instance, the third degree Taylor polynomial, it'll just be the or if I want to find the third degree polynomial, then I'll have to involve adding up all the each of the derivatives. So in this case, it's the nth derivative evaluated at c over n factorial times x minus c raised to the nth. So it's a summation of each of these terms. So we're going to start off with the equation of the tangent line. So simply be f of 2 plus the slope times x minus 2. And then we can start the pattern. The pattern is going to be the second derivative evaluated at 2 over 2 factorial times x minus, the center is 2, so that's why we have the c being 2, x minus 2 squared. Third derivative over 3 factorial times x minus 2 cubed. And then we can just plug all this information that's given to us into our polynomial approximation. So negative 3 gets replaces f of 2. 5 gets plugged in for f prime of 2. F double prime of 2 gets replaced with 3. And then third derivative evaluated at 2 gets replaced with negative 8. Okay. And if we clean this up a little bit more, or we can leave it like this, is essentially 8 over 6, which is 4/3. And then once we have our polynomial approximation, then we can use it to approximate f of 1.5. So we'll plug in 1.5 in for all the x's. So 1.5 gets plugged in for all the x's. This is actually going to be a calculator question. Sorry, non-calculator here. So so we're going to have to just evaluate all this by hand. However, if this is non-calculator, then it's acceptable if you leave your answer in without simplifying. So this will be acceptable. But if we were to simplify this, it'll come out to be negative 4.96. All right, part B. The fourth derivative of f satisfies the inequality that the fourth derivative evaluated at x, the absolute value of that is less than or equal to 3 for all x in the closed interval from 1.5 to 2. Use the Lagrange error bound on the approximation to f of 1.5 found in part A to explain why f of 1.5 cannot equal to negative 5. So what the Lagrange error bound does tells us about the maximum error. Just as a review here, we know that the difference between the actual value of the function at 1.5 and the polynomial approximation at 1.5, the difference between these two is off by no more than this remainder value. And this remainder value is n plus first derivative evaluated at some value z over n plus 1 factorial times x minus c to the n plus 1. So this is going to be the maximum error, or the maximum amount of difference between the actual value and the approximated value. All right, so we know that we're trying to evaluate, we're trying to find the error for the third derivative, for the third degree Taylor polynomial. So we're going to use the fourth degree because it's going to be n plus first. So the fourth degree evaluated at z. So, but we know that the fourth derivative evaluated at some x cannot be any greater than 3. So we know that 3 will be a safe upper bound for this portion of the remainder. So we can replace this expression with 3, and then we know n is going to be 3, so 3 plus 1 factorial is simply 4 factorial. The x in this is the value in question, which is 1.5, so 1.5 replaces x. The c is the center, which in this case they tell us is about x equals 2. So 1.5 minus 2 raised to the 4th, because n plus 1 is 3 plus 1, which is 4. So then the remainder is just going to be, or the maximum error is going to be whatever this value gives us. So 3 over 4 factorial times 1.5 minus 2 is negative 1/2 raised to the 4th. And if we clean this up, this ends up to be roughly about 0.008. So we know that the maximum remainder, maximum error between the difference of these two values is not going to be off by no more than 0.008. So whatever that difference, that approximated difference between the function and the polynomial is not going to be off by more than 0.008. So we know the maximum error is going to be 0.008, and we know that there's no way that the value for the third degree Taylor polynomial at 1.5 can include -5. Okay, and the reason why is because our approximation is -4.96, and then the Lagrange error bound is telling us that this approximation is accurate up to 0.008. So basically it's saying that the exact value is -4.96, give or take 0.008. And so if we create the range that given the error of what these values could be, -5 does not fall into that interval. So if I were to take my approximation, if I subtract 0.008, and if I take that approximation and add 0.008, then the exact value is going to sit somewhere between -4.968 and -4.952. And we see that given the error bound and the max and the minimum is not going to include -5. So we know that this, given the error bound and the approximation, there's no way that this value can reach all the way down to -5. Okay. Part C. Okay, write the fourth degree Taylor polynomial for g of x is equal to f of x squared plus 2 about x equals 0. Use p to explain why g must have a relative minimum at x equals 0. So we want to create a fourth degree Taylor polynomial, and we know that g of x equals f of x squared plus 2, so we can just take f of x, or the polynomial for f of x, and then replace every x we see with x squared plus 2. Okay. So we know that here is f of x. Okay. Here's my Taylor polynomial. So I know this represents f of x. So then f of x squared plus 2 would just mean that I'm going to take every x and replace it with x squared plus 2. So when I do that, I get -3 plus 5. X gets replaced with x squared plus 2, and then I have -2. X squared plus 2 minus 2 squared. And if we clean all this up, we should be able to arrive at the fourth degree polynomial. Now, keep in mind that the fourth degree polynomial doesn't mean that there's going to be 4 terms. It just means that the last term is going to have a degree of exponent 4. So we see that after the third term, we can stop there because the third term has a degree of 4. So here we have our fourth degree Taylor polynomial. Now the next part, it says use p to explain why g must have a relative minimum. Now this is our g of x here. Okay, we can use the second derivative test to help us determine that there's going to be a relative minimum. And what we can do is we can take this g of x and we can find g prime and g double prime, and then use the first derivative and the second derivative evaluated at 0 to help us determine if there's going to be a relative minimum or not. So here's g prime. G prime, I'm just going to take this polynomial and find the derivative. So 5x squared becomes 10x. 3 halves x to the fourth becomes 6x cubed, and negative 3 is a constant, so it goes to 0. So here's my g prime. If I evaluate g prime at 0, meaning if I plug 0 in for x, I'll still get 0. Okay. If I find the second derivative, 10x becomes 10, 6x cubed becomes 18x squared, and if I evaluate the second derivative at 0, I get positive 10, and we know 10 is greater than 0. So what that means is, by the second derivative test, if I have a point where the slope of the tangent line is 0, and also at that point it's part of a concave up graph, right? Second derivative at 0 is greater than 0. So if the slope is 0 and the graph is concave up, then at that point there must be a relative minimum at x equals 0. Okay, let's look at number 4 here. Number 4 says, let f be the function that the derivatives of all orders for all real numbers, and we're given some values for each of the derivatives. We'll write the third degree Taylor polynomial and use it to approximate f of 0.2. We can build Taylor polynomial using the formula given here, the summation of the nth degree nth derivative value at c over n factorial times x minus c raised to the n. And so the first two terms is just going to be the tangent line equation, so f of 0 plus f prime of 0 times x minus 0, and then we can start building the rest of our Taylor polynomial. So the second derivative evaluate at 0 over 2 factorial times x minus 0 squared. The third derivative evaluate at 0 over 3 factorial times x minus 0 cubed. And now, once we replace all the values with what's given to us in the beginning of the problem, we get 5 minus 3x plus 1/2 x squared plus 4 over 3 factorial x cubed. And once we have the third degree Taylor polynomial, we can replace each of the x's with 0.2 in order to find the approximation. So when we do that, we get 4.425, and this is part of the calculator portion, so we can just plug that in the calculator. Part B, write the fourth degree Taylor polynomial for g of x, where g of x is equal to f of x squared. So all we need to do is take the f of x, or the f of x approximation, and replace each of the x's with x squared, because we know that's what we're trying to go after, because that represents g of x. So replace every x we see from the Taylor polynomial with x squared. We get 5 minus 3x squared plus 1/2 x to the fourth. Okay. Part C, write the third degree Taylor polynomial for h, where h is equal to the definite integral from 0 to x of f of t dt. So here we have something that represents f of x or f of t, and if we find the integral of this polynomial, then we'll be able to arrive at h of x. So then all we need to do is go through the power rule for each of the terms. So 5 becomes 5x, 3x becomes 3x squared over 2, 4 over 6 x cubed becomes 1/6 x cubed, x squared, right? So I'm sorry, not this term here. This term, 1/2 x squared, 1/2 x squared becomes x cubed over 6. So we don't have to, we can ignore this term, because part C is only asking for the third degree Taylor polynomial. So we can stop after we see third degree. Okay, part D, let h be defined in part C. Given that f of 1 is equal to 3, find the exact value of h of 1 and explain why it cannot be determined. Okay, so what we can say is that h of 1 cannot be determined because f of t is known only for t equals 0 and t equals 1. Remember that we're told that f of 0 equals 5 and f of 1 is equal to 3. However, we're not told what's happening between 0 and 1. So because of that, we have something to build off of from 0 and 1, but we don't have enough information in order to find the definite integral from 0 to 1, because we don't have information, or the function is not defined from between 0 and 1.